Hello and welcome to the heat transfer course Conduction. This course is brought to you by a cooperation between RWTH Aachen University and the University of Twente. My name is Wilco Roos, and in this video we will look at the topic of fin efficiency. The learning goals in this video are first to have a look on different fins of different material and geometry, and in the second part to look at the fin efficiency, how it can be derived and what the interpretation will tell us of that. So let's go back and review the temperature profile in a fin. We looked in the last video at two classical boundary conditions for the fin type problem. So at x equal to 0, at the fin base, we have a prescribed temperature T bottom, which we can then in an reference temperature, using a reference temperature of TA, rewrite in theta at the location x is equal to theta bottom. On the other side, at the fin head, here at x equal to L, we assume that there's no heat transferred across the upper surface, which leads to the fact that the first derivative of the temperature and also of the reference temperature theta will be 0. This leads to the temperature profile inside a fin. So this newly defined temperature theta is equal to theta bottom, so the temperature difference between the ambient and the bottom, times this function of exponential subfunctions. These exponential functions can also be rewritten in types of a cosine hyperbolicus function, where we have a cosine hyperbolicus function on the top and a cosine hyperbolicus function on the bottom. I will go more into detail on this parameter m in the next slide, but we remember this is a fin parameter. So if we want to draw the temperature profile, we have two known information. So first, we know that the temperature will start here at T bottom, and on the other side we will have a zero gradient here at the location x equal to L. Now the question is still remaining, where is the temperature TA in this diagram? The answer is that is of course below the temperature, because heat is always released from the fin towards the surface. There's not a process vice versa. This cannot happen. But it is also not necessary that the temperature at the fin tip is equal to the ambient temperature. That depends on the length of the fin, and due to this boundary condition we will never reach the state that TA is equal, or T at the location x equal to L is equal to TA. Now, in the next step, I would like to look at fins of different material. So let's start with some kind of convenient material, that is of course copper or aluminum. The thermal conductivity of these materials is very high. So now let's take the thermal conductivity of copper with 385 watt per meter Kelvin. If we construct a fin out of steel, here for instance a chrome nickel steel, a thermal conductivity in the range of 15 to 20 or 30 watt per meter Kelvin is usual. So for chrome nickel steel it is 16 watt per meter Kelvin. And then for glass, some very different material right now, the thermal conductivity of glass is 0.8. So let's see how those type of materials behave if we create or develop a fin as shown here. We have assume a height of the fin of 4 centimeters, so 4 millimeters, a diameter of 8 millimeters, and let's assume a heat transfer coefficient between the surface of the fin towards the environment of alpha equal to 10 watt per meter square Kelvin. What can we do now with this set of information? We can of course look at the type of fin. It's a pin fin, and due to this geometry, our parameter, fin parameter m square is equal to 4 alpha divided by lambda d. Remember, it had something to do with the circumference and the cross-sectional area, this ratio, and then also with the heat transfer coefficient outside and the thermal conductivity, the thermal conductivity of the liquid, excuse me. So now we have the temperature profile in these two different formulations, and we can look at the temperature at the head and the base as two reference points that can be used to draw the temperature profile in the diagram later on. At x equal to 0, of course, we had the boundary condition that theta of x is equal to theta bottom. So there is no surprise with this temperature. On the other side, at the location x equal to L, we can plug this in our equation as shown here on the bottom, on the top, sorry. And if we introduce this value L minus x is equal to 0, here also L minus x is equal to 0, so we end up with the exponent of 0 plus the exponent of 0. Each of those terms is 1, so in total there is 2. And on the bottom we are left with the exponent of ml plus e minus ml. And we can now insert the fin parameter and see what happens if we change the thermal conductivity. Of course, this bottom part will change, and as such we will have different values for the temperature at the fin top. So the temperature of the fin top for the material here for copper, we need to calculate this coefficient m square using the values given. We come to a value of 13 1 per meter, and from the m square calculations we can also calculate m times L, and this value is 0.144. And with the value of ml we can insert this in the equation here above, and we get an information on the ratio between the temperature at the top and the temperature at the bottom. So mainly the temperature difference towards the environment at location L and at the location x equal to 0. And for copper this is 98.8 or even 9%. So the temperature at the tip of the fin is nearly the temperature at the bottom. If we change now to a less conductive material, here chrome nickel with 16 watt per meter Kelvin, we can do exactly the same process and we end up with a value of 79%. So the temperature is a little bit lower compared to the temperature of the bottom, but still not that much difference. Now, the last material was glass with a relatively low thermal conductivity, and if we see that here, we come up to the conclusion that the temperature difference is only 8.5%. As such, the temperature at the fin top is significantly lower compared to the temperature at the base. Now, with this values calculated, we can go into the diagram and try to draw the dimensionless temperature profile for the three different materials. And in order to do that, I would like to start with the glass, and I would like to start with the known locations. So of course we will start here at the theta bottom divided by theta bottom is equal to 1. So this will happen to be one important point, and then the other point is this 0.085. So the difference between the bottom temperature and the surface temperature at the tip of the fin. And now we can draw the line, not very complex. We have the 2 points, exponential decay, a 0 gradient here, and we get to this curve. Now for the other material, for the chrome nickel steel, we can draw the profile in a similar manner, and also for the copper. Remember here the temperature of the copper material is nearly homogeneous inside the fin. Now, what are the findings from this example? So first, the temperature profile, if we know the two endpoints and we know how the spatial course in the fin is like, we can easily draw that and give an impression how the temperature in the fin will be like. Now, second, we're changing the material property in here the thermal conductivity. We see that for highly thermoconductive materials, the fin head temperature is very high, almost the fin bottom temperature. Only for very low materials of very low thermal conductivity, this is different. So the higher the surface temperature of the fin, the more heat is of course transferred. This is also an important implication. And now the last finding, or it's more a question, what fin is better, made out of copper or made out of glass? And for this we will look into the topic of today, the fin efficiency. How do we define the fin efficiency here? We say, okay, the fin efficiency is the actual heat transferred from the fin divided by the maximum amount of transferable heat. And I will come to that definition in a few moments. So for a real fin, we see that the temperature here at the bottom is higher than the temperature at the tip, and as such, more heat is released over the surface here on the bottom and less heat is released on the top part. Now we assume, or we define that the maximum transferable heat is achieved when the temperature remains equal from the base of the fin to the top of the fin. And in this case, then the temperature in the entire fin is equal to T base. So it's not a function of the location anymore, and the heat transferred from an ideal fin would look like this. At any location, the heat that is released to the ambience is equal. Now, in order to calculate the fin efficiency, we need, of course, now to calculate both the heat transferred from the fin and the maximum amount of transferable heat. Let's start with the upper part. So we need to calculate the heat that is transferred across the entire fin surface. So what we could do, we do an integration of the convective heat flux over the entire surface. So we need to have the convective heat flux at any location x, and we have to integrate it from 0 to L. This is a little bit complex because we then again need to integrate our complex function of t of x, or the theta of x function. And as such, I would like to use an alternative approach, because we know that the entire heat that is transferred across this surface needs to go into the fin from the bottom part. So the convective heat loss is equal to the conduction here at the fin base. And this is much easier to calculate because we know that from Fourier's law, the heat that is conducted through the base is equal to minus lambda times the cross-sectional area times the temperature gradient at the location x equal to 0. Or because the temperature gradient at x equal to 0 is equal to the temperature, or the gradient of the reference temperature here, theta, so d theta dx, we can also use this expression, and this requires just to differentiate our temperature profile by x. The temperature profile was given by this equation, and so to make the derivative, we see that here we have x in the top part, and then at the location x equal to 0, you see that we have already put in 0 for the x, and due to the differentiation of exponent minus m, we will attain a minus here on this part, and an m in both cases, so we can write the m in front of the equation and get now an equation for the first derivative, which then can be inserted in the Fourier's law of the heat conduction, and we have now an expression for the heat transferred by the total fin, which of course depends on the cross-sectional area and the thermal conductivity, as well as on the fin parameter and the temperature difference at the bottom. Now, how can we calculate in the next step the maximum amount of transferable heat? We do the same approach. We start with an integration of the heat that is transferred across this surface. And now we have to integrate. We cannot get along with that problem. But interestingly, we said, okay, the temperature is constant. So because the temperature is constant, also this theta bottom is constant from 0 to L. And so the integration of theta bottom over the length 0 to L is just theta bottom times the length L. And so the maximum amount of heat that can be transferred is equal to pi times the diameter times the alpha theta bottom times L. What do we see here? Pi dl is equal to the circumferential area of the whole pin fin, and then we have the heat transfer coefficient and the temperature difference between the pin fin and the environment. So having calculated the heat transferred from the fin and the maximum amount of heat transferable, we can set this into the relation to each other and calculate the heat transfer coefficient eta. So doing that, inserting the values, we have here on top a part and on the bottom a part. I don't want to go into name all the variables again, but what we see is that we have lambda AC, and here on the bottom we have alpha times pi and d, and this remembers a little bit on the fin parameter m. So let's look. The fin parameter m was 4 alpha divided by lambda times d, and that's actually what we see here, except of the 4. So we can add this here, and we see that we can replace this part here by the fin parameter, and we can also remove the theta bottom because that's happening twice, and from that we can calculate that eta, the fin efficiency, is a tangent hyperbolicus of ml divided by ml itself. Now this is the derivation of the fin efficiency. How can we draw that? So in order to draw that, I think it's best to recall the course of the tangent hyperbolicus function, and that's shown in this diagram. So the tangent hyperbolicus is 0 for x equal to 0 and approaches asymptotically the value of 1, and already at the value of 2 this has nearly approached its value of 1. So it has a steep gradient here. Now if we do now the drawing for the diagram of the fin efficiency versus the fin parameter ml, we should first see what happens for large values of ml and what happens for low values. So for large values, we can see here there is L goes to infinity, so the tangent hyperbolicus of ml approaches 1, and as such the fin efficiency decreases by 1 over ml. For short fins, the fin efficiency is 1 because we have these two parts. They both go to 0 for eta equal to 0, but they the expression tangent hyperbolicus of ml divided ml approaches 1. So our fin efficiency profile looks like the following drawing. Now let's recapitulate once again the fin parameter for the different cases. So the fin parameter, as it was described or developed, was alpha times the circumference divided by lambda times AC, and for a plane fin that resulted in m is approximately 2 alpha divided by lambda delta by a factor of 1/2. Remember that we were able to cross out the depth of the fin, and the parameter delta stays that defines the cross-sectional area. So for the pin fin, it was 4 alpha divided by lambda d as well. We used this all the time in this video, and now with these two values we can have a look how the physical dependencies are. So we see in all cases that the thermal conductivity is on the bottom, alpha is on the top, and so what happens with the fin efficiency, if for instance the material thermal conductivity increases, then of course m squared decreases because it's here on the bottom, and as such the fin efficiency increases. Very clear, we have seen for copper, high thermal conductivity, the temperature is nearly homogeneous, so it's increasing. What happens if we increase the length of the fin? Then what happens if we increase the diameter of the fin? This results in the fact that also m square increases and the fin efficiency increases as well. If we, on the other hand, increase the length, then of course what happens is that the fin efficiency decreases. And then we have one other parameter, the convective heat transfer coefficient. If alpha, for instance, decreases because the fluid flow becomes slower or we change the fluid media, then it's the same that m squared decreases, the temperature becomes more homogeneous and the fin efficiency increases. What are limitations in the interpretation? So what the fin parameter tells us is how homogeneous the temperature is inside the fin. So it's a measure of how effective is the upper part of the fin, where the temperature has already been reduced compared to the bottom temperature, and how is this heat transfer compared to the heat transfer of the fin at the bottom. So ETR, the fin efficiency, does not provide information about the total heat that is transferred, although it decreases when the fin is extended. So if we increase the length of the fin. Let's finish this video also with a few questions. First, what relationship does the fin efficiency describe? We have seen that the fin efficiency describes the ratio between the heat actually transferred from the fin to the maximum amount of heat that can be transferred. This brings us directly to the second question. What is the assumption for the theoretical maximum transferable heat of a fin? And the assumption is that the entire surface of the fin is equal to the bottom temperature, and as such, the heat that is released from a part of the surface on the fin tip is exactly the same, or shows the same efficiency than the another part of the fin on the bottom. How can we increase the fin efficiency? We have seen that with the different variables. We have seen that if we increase the thermal conductivity, the fin efficiency increases because the temperature becomes more homogeneous. If we increase the cross-sectional area, the fin efficiency increases. But for instance, if we increase the thermal heat transfer coefficient due to a higher fluid flow velocity, then the fin efficiency decreases. And also if we increase the length of the fin. With that, I would like to thank you for your attention and see you in the next video.